Hey everyone, welcome to the first video in a series that's going to be all about grade 12 calculus. And my main goal with this series is to go over the main concepts that you'll find in the course, and hopefully that gives you a strong foundation to understand the course as a whole a little bit better. Now, the first concept I want to talk about is definitely an important one, and that is the concept of limits. And a limit is the value that a function approaches as the input approaches some other value. So in other terms, our y value on a function or on a graph is getting closer and closer to a certain value, just as its x value does the same. So if I look at the first graph here, I just have a regular linear equation, and I plotted the point 6, 4 on the graph. So obviously we could say that when x equals 6, y equals 4. But what about when x is approaching the value of 6? And that's what, the value getting closer and closer means. So if I were to draw an arrow on the left side, we could assume that we're kind of like on the line here, and we're getting closer and closer to our point. We could say that as we approach x equals 6, we are also approaching the y value of 4. And we could say that that is the same on both sides of the point. So if we're approaching from the left, we can see that we're getting closer and closer to a value of 4. And the same thing is true if we were approaching from the right. And this is one of the core rules of limits, is that our left-hand limit must equal our right-hand limit in order for it to exist. So we've noticed on the graph that the value we approach on the left is the same as the value we approach on the right. And in both cases, we are approaching a value of 4. So if I wanted to write this out a little bit more professionally, let's say, I could say that this equation, or this function, is represented by the equation y equals x minus 2. And that's just a simple line equation. And then to represent its limit, I could say that the limit as x approaches 6, and that's what this arrow means, we're approaching this value, of x minus 2 equals 4. And so this would be probably the cleanest way to represent a limit. Okay, let's look at the second example here, and it's a little bit different. And I'm just going to draw an open-ended point there. And I want to focus on the x value of -1. This is an example of a piecewise function. So a piecewise function is basically a function that is being represented by 2 or more different equations, depending on where you are on the graph. So this section here, basically from -infinity all the way to -1, is being represented by this line. And then everything beyond -1 is being represented by a different line. But what if I wanted to look at the limit as x is approaching -1? Well, if I'm approaching from the left, I would be going up this line here, and I would be approaching this point where y equals 2. So I could say that in this scenario, the left-hand limit is approaching 2 when we're approaching x equals -1. But if I do the same thing approaching from the right, I can see that I'm getting closer and closer to this open-ended value here, which looks like a y equals 4. So in this case, the right-hand limit would be 4. Since the left-hand limit does not equal the right-hand limit, we would say that the limit does not exist. And this is super common on a piecewise function because there's going to be some sort of a gap or a jump between 2 points. And so if we approach a value from the left compared to from the right, we should be approaching different y values. So that's when we had a graph, but what if we only have an equation? Then we're going to have to think algebraically. So you can ignore these limit properties here for now. I will go over them in a bit. I just wanted to show you them right now so that you can kind of take a look at them and maybe start to piece together what they represent. But let's just look at the equations we have here. So y equals x minus 2. And let's use the same example that we had last time. So let's say we want to look at the limit as x approaches 6. We already saw on the graph that our answer is going to be a 4. And what we can do here is I can literally just plug in my value of 6 for x and get the same answer. So for simple limits, you can really just plug in the x value you're approaching into the equation and get an answer. And if we do the same thing over here, x squared plus 5, let's say I want the limit as x approaches 2. What I could do is I could just plug in the value for 2 and solve for y. So if we can just plug in the value for x that we're approaching into our equation, why would we need to learn anything else in terms of algebraic properties of limits? That is a very good question. Number one, some questions, especially later on in the course, are going to require you to use limit properties in order to solve them. You won't be able to simply plug in the value for x. For example, if your value of x that you're approaching is infinity, it might be a little confusing to plug in a value of infinity into the equation. So that's when we need some help on that. Another example would be when the equation is actually undefined at the value that you're approaching. So it is important to know them. So let's go over how we would represent these equations with these algebraic properties. So the first one I want to look at is down here. And that just tells me that the limit of an equation can basically be split into two different parts if I represent each part as a function. So if I look at y equals x minus 2, and let's say we wanted to find the limit as x approaches 6 for x minus 2, what I could do here is I could actually break this apart into two different limits. So you can see here that the limit of a function here is equal to one piece of the function being defined at a limit plus or minus the other piece. Here they're just representing the pieces of a function as f of x and g of x as two separate functions. So in this case, I have a limit as x approaches 6 for x and for 2. If I look at the first property here, as x approaches any value for a constant c, my limit is just going to be the constant value. So the limit here for 2 is just going to be a 2. Now if I go down, or actually to the right here, the limit as x approaches a value for x on its own is just going to be that value. So I could say that the limit here for x is a 6, and 6 minus 2 is, you guessed it, 4, which is the same answer we got up there. It gives you the same answer. It's really just a matter of notation. You're showing maybe on a test how you're able to break down an equation or a function by using algebraic properties to find a limit. Let's get a bit more practice in. So on this one here, looks a little bit more complicated. In the same vein, we could literally just plug in a value of 2 here and get our answer. But let's see if we can use our properties. In this case, we have a 5x squared being multiplied by a 3x. And that means that this algebraic property is going to be very useful. And it tells me, just like before, where if I were adding or subtracting two different chunks of a function, I could separate them into two separate limits. I could do the same thing with multiplication. So I can rewrite this like so. All right. Now I'm going to go back and get another property that will be useful here. This one right here. So it's showing that if I have a constant, or basically a coefficient, in front of the chunk of the function that I'm working with, I can basically pull it out and have it separate from my limit. So if I look at the 5x squared, I could rewrite this as 5 times the limit as x approaches 2, or x squared. So I've just taken this 5 and pulled it out of my limit. And I could do the same thing with my second part and just have an x. So we know that when an x is by itself, it's just going to take the value of what we're approaching on x. So this is going to be a 2. And then we can't forget to times it by 3, because that's the value we pulled out beforehand. So I'll put that in brackets. And then if I look at the first chunk here, I have an x squared, so I can't just plug in my value of 2 and call it a day. I need to look at the power property, where I can basically rewrite my limit just with an x, and then raise the entire thing to the power of 2. And that's what this property is showing, where I'm basically taking out the exponent, making a limit with what's left, and then applying the exponent on the entire answer. Once again, we have an x by itself, that's going to equal a 2. So now we have 5 times 2 to the power of 2, because this whole part needs to be to the power of 2, times 6. This will be a 5 times 4 times 6. And my final answer should be 120. And once again, if I just plugged in a 2 way back here, I would have gotten the same answer. So I'm going to leave this example here for you to try on your own. You are going to have to use this limit property here. Very similar to the multiplication property. It's just that we're doing the same thing but with division. So I will let you give that a shot. What I want to focus more on are scenarios where we can't just plug in our x value. So what if setting x to our limit value does not work? So this is an example of a discontinuous function, just like the piecewise function we were working with before. And you may notice we have a bit of a gap right in the middle here. And that has to do with the equation. So I have an equation for the line here. If I set x equal to 3, let's see what happens. I get 0 divided by 0. And that is no good, because that means that our function is undefined at that point, or at that x value. Now, when we have a 0 over 0, that means that we have a point discontinuity. And what that means is we basically have a pretty standard function, but there's one point on it that is not defined. So it's kind of got a gap in it. So if I have a graph for this function, it's pretty easy to see that the limit can still be defined, even though the function is not defined at x equals 3. So I cannot plug x equals 3 into the equation, but it's technically still approaching some value at x equals 3 from the left and from the right. And based on the graph, it looks like that would be a y value of 3. So that's a super important concept to understand. Even if a function is undefined at an x value, it can still have a limit as it approaches that value. Now the question is, how are we going to solve for the limit if we didn't have the graph? So let's rewrite what we're trying to do here. Once again, if I just plug in the 3 here, I'm not going to get anywhere. What I can do is manipulate the function to see if I can get rid of this undefined value. So I'm looking at the x squared minus 3x. What I could do is just pull out an x, factor that out. And now, hopefully you remember from grade 11 how to simplify rational functions or rational expressions. We are able to cancel out the x minus 3 that we have on the top and bottom. So we're left with an x. And then going back to our trusty algebraic properties, we know that in this scenario, our x value is just going to be the value that we're approaching. Therefore, our limit equals 3. So that's how we could do it if we didn't have this graph over here. Last example I want to do, we have a u as our variable instead of an x, but that's fine. That's just a notation thing. And if I plug in a value of 2 for u, I'm also going to get the scenario where I have 0 over 0. So I need to think of a way to kind of manipulate this and simplify things. What I can notice here is I have actually a difference of cubes up here. I have u to the power of 3 minus 8. And I'm actually not sure if in grade 11 you go over how to expand a difference of cubes. So I'll quickly go over that now. Basically, there is a pretty solid pattern you can use. The first part of our answer is going to require the cube root of this first term here. So if I took the cube root of u to the power of 3, I would just get a u. And I'm also going to need the cube root of my second part, or my second value, which in this case is a negative 8, and that would give me a minus 2. The second bracket is going to also require us to use these values that we found. So we have a u and a 2. I'm going to square root the first value, so I get u squared. I'm going to square root the second value, so I get a 4, and I'm going to put that on the end here. And then in the middle, I'm just going to multiply together the 2 original values that I got up here. So I'm going to have a 2u. And if you want to double check your work, you could also just expand out these 2 brackets together and see if you get back to your difference of cubes. But anyways, let's get back to the question. Once again, we have some brackets that we can cancel out. So we are left with u squared plus 2u plus 4. And now, since I've gotten rid of the denominator and I've moved things around on the numerator, I should be able to plug in a value of 2 for my variable and solve for my limit. Or if you want, you could make things a bit more cumbersome and use the algebraic properties. But I do know that just plugging the value in here will work. And we get an answer of 12. So if there's one part of limits that you should really focus on, it's definitely how to solve these kinds of questions where you have an undefined point at the x value that you're approaching, because it's going to take a little bit of practice and a little bit of creativity to think about how to manipulate the equation to get a solvable answer. Thank you so much for watching the first episode in this series. Stay tuned for the next video, which is going to be all about how to solve for the rate of change of a function based on the concept of limits. Thanks, and take care.